everybody, I'm Bhumika. Now this is part 2 of end semester exam solutions. So question 6, linear regression coefficient estimation. So closed form solution is the normal equation provides an analytical solutions by minimizing the cost function directly. So this is the value of theta, where theta represents coefficients, x is the feature matrix and y is the target vector, and this method computes optimal parameters in one step but becomes computationally expensive for large data sets due to matrix inversions. Now gradient descent क्या होता है? An iterative optimization approach that updates coefficients using partial derivatives. The learning rate alpha controls step size. Batch gradient descents uses all training examples, while stochastics variance update per sample for faster convergence on large data sets. Now, logistic regression fundamentals. Logistic regression is a classification algorithm that models the probability of binary outcomes using the logistic sigmoid function. Unlike linear regression, it outputs probabilities between 0 and 1. First, linear combination and apply sigmoid function. Third, interpret probability. इसमें predict class 1 को predict करते हैं, otherwise 0 को करते हैं. Like for example, for input features yielding z equals to 2.5, probability equals to 1 by 1 plus e to the power minus 5.5, which is similarly equal to 0.924, strongly indicating class 1. So वही in their linear combination, इसमें हम weighted sum को calculate करेंगे, then उसको ट्रांसफॉर्म करेंगे z को यूजिंग दिस फंक्शन एंड फिर उसके बाद प्रोबेबिलिटी को इंटरप्रेट करेंगे. नाउ k मीन्स क्लस्टरिंग एल्गोरिथम. सबसे पहले इनिशियलाइज k सेंट्रोइड्स, रैंडमली सिलेक्ट k डेटा पॉइंट्स एज इनिशियल क्लस्टर सेंटर्स. कॉमन मेथड्स इंक्लूड रैंडम सिलेक्शन और k मीन्स for better initializations. Now assign each data points to nearest centroids using distance matrix, typically Euclidean. This is the formula. Now recalculate centroids as mean of all points in each cluster. C equals to 1 by n summation to x for all points in cluster J. Iterate until convergence. Repeat assignment and update steps until centroids stabilize or maximum iteration reached. Impact of initial centroids. Initial centroids placements critically affects final clusters and convergence speed. Poor initialization can lead to suboptimal local minima. K-means addresses this by spacing initial centroids apart, improving both quality and convergence rate significantly. Now, K nearest neighbor algorithm. Step 1, we have to choose K. Select number of neighbors, typically odd for binary classification to avoid ties. Common values 3, 5 or 7. Step 2, calculate distance. Now compute Euclidean distance from test point to all training points. Then find k nearest, sort distance and distance k training samples with smallest distance to test points. Step 4, classification. Majority vote among k neighbors. Regression is average of k neighbor values. Key consideration: KNN, that is K nearest neighbor algorithm, is a lazy learner, no training phase, but requires storing entire datasets. Feature scaling is crucial since distance phase. Now Tree-based methods comparison. Decision trees. Strength, highly interpretable with clear visualization. Handles both numerical and categorical data. Requires minimal data pre-processing. Non-parametric, no distribution assumption. Capture non-linear relationship naturally. Now its weakness, prone to overfitting on complex data sets. High variance, small data changes alter tree, bias towards dominance classes, struggles with XOR type problems, not ideal for extrapolation beyond training range. Now random forest, its strength, reduce overfitting through ensemble averaging, handles high dimensional data effectively, provides feature importance ranking, robust to outlier and noise, works well without extensive hyperparameter tuning. Its weakness, less interpretable than single decision trees, higher computational cost, many trees, increased memory requirement, slower prediction time compared to single models, can still overfit on noisy datasets. Now boosting strength, achieves state-of-the-art accuracy on many tasks. Sequential learning corrects previous errors. Handles imbalanced datasets well. Built-in regularization prevents overfitting. Flexible loss function for various objectives. Its weakness, sensitive to hyperparameter selection, longer training time, sequential nature, can overfit if carefully tuned, more complex to interpret and debug, vulnerable to noisy data and outlier. Now, big data processing framework, Hadoop ecosystem, Apache Spark. That is Hadoop distributed file system stores large datasets across multiple machines with replication for fault tolerance. Data splits into blocks, typically 128 MB. Yarn, yet another resource negotiator, manages cluster resources and schedules jobs. Separates resource management from processing logic. MapReduce, programming model for parallel processing. Map phase processes data in parallel. Reduce phase aggregates results. Disk-based operation. Spark uses in-memory computing with resilient distributed datasets (RDDs) for faster processing. Driver program distribute tasks to executor nodes across the cluster. Advantages over MapReduce. Its speed up to 100x faster due to in-memory operations. Easy to use. High-level APIs in Python and Java. Unified platform, batch streaming. Interactive supports real-time queries and iterative algorithm. Lazy evaluation. Logic gates from neutral network. Here logic gates and or not XOR, minimum 3, 2 hidden plus 1 output, and here 1 1 1 steps sigmod, wait 1, wait 2, wait 3. Here requires hidden layer combination, not required. Key insight: XOR is the classic example requiring multi-layers networks. It cannot be solved by a single perceptron, demonstrating the need for deep learning architecture. Neutral network architectures comparison. Conventional neutral networks (CNNs), composed of convolutional layers, feature abstraction, pooling layers, dimensionally T-reduction and fully connected layers classification. Uses shared weight and local connectivity. Its application: image classification, object detection, facial recognition, medical image analysis, autonomous vehicles, video processing. Recurrent neural network (RNNs) contains feedback loops allowing information persistence across time steps. Variants include LSTM (long short-term memory) and GRU (gated recurrent unit) to handle long-term dependencies. Applications: natural language processing, speech recognition, machine translation, time series forecasting, sentiments analysis, video captioning. Now, advanced neural network paradigms. Generative adversarial network. Two competing networks generators create synthetic data for random noise. Discriminator distinguish real from fake. Train adversarially until generator produces realistic output. Application: image generation, style transfer, data augmentation, super resolution, deepfakes, drug discovery, synthetic data creation. Transfer learning leverages pre-trained models, that is ImageNet trained CNNs as starting points, frees early layers and fine-tunes later layers on target tasks. Require minimum architectural changes. Application: small datasets problems, medical imaging, domain adaptation, few short learning, rapid prototyping, specialized classification tasks. CNN and RNN are specialized architectures for spatial and temporal data respectively. Thank you everybody.